In this video, we present the synthesis of Tegoprazan, a drug belonging to a new class of anti-ulcer drugs, the potassium-competitive acid blockers, abbreviated as PCABs, according to the retrosynthesis presented in the previous video. This synthesis is characterized by the parallel preparation of a substituted benzimidazole and acromin as key intermediates from accessible raw materials. Also, it highlights the use of the Mitsunobu reaction between the two intermediates to obtain the drug with the desired stereochemistry, as we will see later on. Preparation of the substituted benzimidazole through the Pinner reaction, consisting of the addition of benzylamine 2 to acetonitrile 1, imidine hydrochloride 3 is generated. Treatment with molecular bromine in an acidic medium of the diketyl 4 yields bromomalonaldehyde 5. The nucleophilic substitution of the bromine in 5 by the nitrogen of the amidine 3 forms the intermediate 6, which, after an intramolecular addition of the amino group to the carbonyl group, quantitatively generates formilimidazole 7. Through the Staube condensation between aldehyde 7 and diethyl succinate 8, the unsaturated succinic acid derivative 9 is prepared. Activation of the carboxyl group by reaction with acetic anhydride to form the mixed anhydride and subsequent intramolecular aromatic acylation yields benzimidazole 10. Hydrolysis of ester 10 produces carboxylic acid 11, which reacts with thionyl chloride to generate acid chloride 12. Treatment of acid chloride 12 with aqueous dimethylamine yields amide 14. Preparation of chiral chrominol. Regioselective aromatic nitration of metadifluorobenzene 15 is performed with hydrated iron nitrate using hexafluoroisopropanol as a solvent and activator, yielding nitrobenzene 16, which, upon reduction with hydrazine hydrate in the presence of nanoparticles of palladium supported on a polyethylene glycol polymer, yields the difluorinated aniline 17 almost quantitatively. The presence of the amino group in 17 serves to direct the aromatic bromination that is carried out with molecular bromine. In the presence of acetic acid, favoring the preparation of the aniline derivative 18. Once its function is fulfilled, the amino group is removed from the benzene ring by first generating the diazonium salt through reaction with sodium nitrite in an acidic medium, and then reducing it with hypophosphorus acid to prepare bromodifluorobenzene 19. The substitution of the bromine atom in 19 with a hydroxyl group is carried out with potassium hydroxide at a high temperature to generate phenol 20, which, when treated with potassium carbonate, forms the corresponding phenolate, and upon adding chloropropanyl 21 to the reaction medium. Through a Williamson-type etherification, it forms ether 22. The oxidation of the primary alcohol in 22 is performed with sodium hypochlorite and sodium chlorite to yield the carboxylic acid 23. Intramolecular acylation is performed with polyphosphoric acid to generate chrominone 24. Through Noyori asymmetric hydrogenation, chrominone 24 produces chiral chrominol 25 with an R configuration. Next, the key reaction of the synthesis is carried out, the Mitsunobu etherification between phenol 14 and the chrominol 27 in the presence of diisopropyl azotocarboxylate and triphenylphosphine to prepare the chiral ether 26 with inversion of configuration. In this reaction, the phosphine initially adds to the double bond of the reagent to form betaine A. The hydroxyl group of 25 nucleophilically attacks the phosphorus, producing the phosphonium salt 27, where the result has been the activation of the hydroxyl group in 25 as an excellent leaving group. Once the hydroxyl group in 27 is converted into a good leaving group, the nucleophilic attack of the hydroxyl group of 14 to the chiral carbon in 27 results in the chiral ether 26 with inversion of configuration to obtain the desired stereochemistry in the final product. Finally, the nitrogen of the imidazole ring in 26 is deprotected. This is achieved by palladium on carbon-catalyzed hydrogenation to synthesize tegoprazan with a 94% yield. In summary, here are the main reagents and intermediates, along with their structural contribution. Thank you for your attention.